morning. Anybody have any questions that Rich knows about power system stabilization? It's pretty phenomenal, and that's kind of the point of my paper. We're seeing in the past 20 years different system architectures that I wanted to kind of evaluate and maybe not press one over the other, but just give you things to think about when you select a system architecture. Like Johnny, I've probably got more war stories in 20 years than I do slides, but I've been in about 152 hydro plants. Fortunate enough from Labrador to Africa and some other things. If you remember years ago, originally power systems or power plants had separate, distinct, discrete systems that took care of all the different functions of the powerhouse: excitation, AVR, synchronizer, governor, protective equipment. They also had a big, massive set of relay logic that did this and that and sequenced. And lately, it seems like there's a trend to combine all these systems into one big master blaster. We call it PLC, that does all these functions combined. And in some places that seems to work, combining all the different functionality. But the point of this paper was to identify the specialties in that history of 100 years of governor history or 100 years of excitation history. That expertise is available. And these are some of the papers that are presented in this HydroVision. Some of the other ones, automated regression methods for turbine and spot modeling and simulation. One of the papers that is being presented. This paper we just heard. But the point of this slide is to really get people to think that there's specialists out there, the expertise is out there. Some plants that I worked in that did have a successful master plant controller are typically very small plants. This happens to be two 500 kW machines that the original governor, the original plant equipment was aging and they needed to be replaced. And they did a master PLC automation of the whole plant, and it takes care of everything in the plant, remote and local, from trash rack alarms all the way through breaker commands. In this application, this little small plant was successful with a single PLC that ran everything. If you see, this is part of an old Woodward gate shaft, and this is the terminal lever. They automated with basically it's a jack screw, and the governor function, the fly ball function of that system doesn't exist anymore. There's the plant PLC. Basically is just a gate positioner now. So yeah, it's two small units, but those two small units, that's 500 kW, that doesn't contribute its fair share. It's two 500 kW back into grid stability for speed regulation. That's a lot of different papers, but some other examples I wanted to go to were things that we've seen are plants that did a master PLC consolidating everything, one system that kind of didn't work, and some things to think of, things to look for. We were involved in a powerhouse that had 220 megawatt units that did a full plant automation. Excuse me. And the customer was kind of questioning a few things and wanted some double checks and asked us to come in and evaluate some of the things in just the governor, a small little subsection of the software. And we had about 90 things, 90 deficiencies that were just oversights, because the process engineer was a process engineer, and he's used to looking at the entire plant. He can start pumps and monitor air compressor pressures, but some of the things that were speed control related were just phenomenal. We couldn't believe some of the things we saw, and I won't name the plant. These guys won't name the plant either, but I want to go through some of these oversights that we discovered. This plant has speed switch, proximity probes, and we monitor CTs and prox probes. If one fails, we go to backup channel speed and different things like that. This system had speed channels, but if they had a fault on their input for speed, they didn't know about it. So, if you're in speed governing world, it's like, what? It's bizarre that you wouldn't think of that. This plant had redundant E-highs, and that's an electro-hydraulic interface that have basically two electrical pilot valves on their relay valve for redundancy. And the plan, everything works well, is if you lose a proportional valve or lose an E-high, the control system will swap to the backup. And that worked, but the control didn't know, it didn't tag out the failed E-high. So if you imagine, if you lose an E-high and the system automatically switches to the backup, if the backup fails, the system didn't know not to switch back to the first. So you got this, anybody old enough to remember Pong, the first ping pong game, you got this ping pong thing going back between control valves, and you have no control until something else takes that unit off. I won't go through every single one of these, but they're just, if they wanted to go into a maintenance mode and the gates were at 50%, say in a test situation, you couldn't enter maintenance mode. And the report stated that the problem that you might want to look for in maintenance mode is why the gates don't close. So some of the things that are just oversights. Their gate set point went to 80% when you exit maintenance mode. You switch from maintenance mode back to auto, the gates went to 80%, and you can't do that. Gate position switches weren't fail-safe. If you lost speed, you couldn't drive that gate position function, and some of those were critical shutdown functions. Some of these things are just, we couldn't believe that we were seeing them in the software, because it's just oversights, and it's somebody that's not an expert in their field that's combining all this into a process controller.